Okay, hello everyone. Welcome to our weekly seminar at Jagiellonian. Today our speaker is Raphael Steiner. Well, Raphael is currently at ETH Zürich. He finished PhD in mathematics in last year in 2021 at TU Berlin. So I remember that Raphael, from our joint time in Berlin, that Raphael is very much into directed graphs, combinatorics of directed graphs, both from structural and extremal standpoints. Yeah. I remember your work with Sebastian, never-ending meetings, and but I did browse your webpage now, and I see that you are really active and expanding. So I don't really know what you're doing these days, but I see that graph colorings becomes your topic, yeah, and some aspects of structural graph theory there. So we will see something today clearly from the title, right? So thank you for joining us today. We're really glad, and go for it, Raphael.
Yeah. So thank you, Piotr, for inviting me here. Yeah, so the talk is, as you can see, about the relatives of Hadwiger's conjecture, as I put it. So basically, I will first give a brief introduction on Hadwiger's conjecture, and then for the rest of the talk, present some new results about variations of it. Okay, so let me start the talk right away with some basic definitions, which most of you have seen somewhere, but let me recall them quickly. So what are graph minors? So I guess the standard definition most of you have heard is the thing I've written at the bottom here. By the way, can you see my mouse here? If I point on something, you also see it. Okay. So we say usually that the graph G contains another graph H as a minor if we have a sequence of graphs, G1, G2, and so on, starting with G and ending with H, such that in each step we basically modify the graph only by either deleting something, a vertex or an edge, or by contracting an edge. And there's an equivalent way of putting this definition, which is more useful sometimes. And also here in this talk, I will use this one, which says that the graph G contains H as a minor if in the graph G, I can find a vertex disjoint collection of subsets. So for every vertex in H, I have a representative so-called branch set X subscript H. And they have the property that they induce connected subgraphs of G. So this means basically that if I contract all the edges inside these branch sets, I will get the vertex corresponding to vertex of H. And in order to really get, after this contraction, H as a subgraph, I wanted for every edge between two vertices H1 and H2 in H, the corresponding to branch sets XH1 and XH2 are connected in G by at least one edge, directly linking a vertex in XH1 with a vertex in XH2. So I think pictures say more than words. So let me give some very small examples. So in this graph, for example, I have, so the left-hand side graphs always have this right-hand side graphs as minors because I can select these yellow branch sets and then these induced connected subgraphs, I can contract them, and I definitely will preserve at least those edges shown on the right. Yes, so this is a graph minors. And why are graph minors interesting? So for example, they have some nice properties that they preserve some embeddability on surfaces like graphs of bounded genus or something, planar graphs, and therefore sometimes these classes can also be characterized by forbidden minors. But there's also this approach we will be taking this talk that in particular in graphs which don't contain the complete graph on T vertices as a minor, they appear in this famous Hadwiger's conjecture, which is related to graph coloring, and that's what I will talk about now. So Hadwiger conjecture is already in 1943, so this is by now already quite an old conjecture. And it's basically a generalization of the four-color theorem. So formally it says that if I have an integer t and the graph G does not contain kt as a minor, then I can properly color it with t minus 1 colors. And there are some simpler subcases of this if t is very small. So for example, it is known that if you have no k4 minor, then you always have a vertex of degree 2. These are two degenerate graphs, series parallel graphs, and then you can always easily greedily free color them. But already the next step, if you put t equals 5 here, implies that all k5 minor free graphs are 4 colorable. And we all know that planar graphs in particular don't contain k5 as a minor because k5 is not planar. And therefore, this is a strengthening or an equivalent statement to the four-color theorem, which we know does not have a simple proof so far. So we should not expect Hadwiger to be a very simple problem. And if it is true, then basically for every value of t which is at least 5, this is a strengthening or a generalization of the four-color theorem. So what is known for this exact form of Hadwiger's conjecture? So the only thing beyond the four-color theorem, or the case t equals 5, is that it's proved for t equals 6. Robertson, Steiner, and Thomas showed that k6 minor free graphs indeed are properly 5-colorable. But this is already a long time ago, and it seems very hard to push this further. Already this proof is very complicated and also uses the four-color theorem as a black box. Right. So because this exact form of Hadwiger's conjecture so far seems out of reach, what people also have naturally tried is to give asymptotic bounds. So if t is large, what can we say about the asymptotic bound or the number of colors needed to color the kt minor free graphs? And so what was the best known bound for a long time is by the approach of degeneracy coloring. So we can ask simply by giving an upper bound on the number of edges in kt minor free graphs. So what is the maximum average degree of kt minor free graphs? And Kostushka and Thomason proved in 1984 that this is bounded by some constant times t times square root log t. So this is actually a very slow growing function times t. So it sort of comes close to a linear bound. And then this also gives an upper bound on the degeneracy of these graphs. We can always pick a vertex with at most that many neighbors, remove it, color the rest of the graph inductively, and insert it again, and give it a color which does not appear in the neighborhood. And therefore, this also gives an upper bound on the quadratic number of the form O of t times square root log t. And this is a very natural approach to color these graphs, and it's not so easy actually to improve this bound substantially, in particular not asymptotically. And as I said, for a long time, no one really knew how to do better than this degeneracy approach for coloring. Later on, I will tell you that there was some recent progress, which probably most of you anyways have heard of, that actually improves upon this barrier with the degeneracy, but I will have this on some later slide. One thing which is actually worth mentioning is that this approach with deleting vertices of small degree cannot be improved in itself. So there are graphs which don't have a kt minor for large t and have a minimum degree of t times square root log t, and you can obtain examples of such graphs by considering certain random graphs of a well-chosen size. Okay, so this is just a very brief summary of what Hadwiger's conjecture is and means. And because it's so difficult and important, I mean, lots of work has been built around this conjecture. And there's also some variations, strengthenings, and relaxations of it. And in this talk, I will basically look at two conjectures, which both are kind of like strengthenings in some sense, and yeah, tell you some new results there. So the first part will be about the so-called odd Hadwiger's conjecture. This is a strengthening of the Hadwiger's conjecture by Gerards and Seymour. And yeah, let me tell you what are odd minors, because this is basically how we get there. So odd Hadwiger conjecture strengthens the Hadwiger's conjecture by not only excluding kt as a minor, but making somehow a less restrictive assumption that the graph does not contain kt as an odd minor. And so let me explain how we get to this definition. So basically, the idea of odd minors in general is that in some sense, you can see that for very small examples of t, requiring that you don't have a kt minor is in some sense too restrictive. So for example, if you look at the case t equals 3, graphs without a k3 minor are basically just the graphs without cycles, so forests. And forests, of course, can be two-colored in many ways, but we all know that there's a much nicer and richer class of graphs which are two-colorable. We know exactly which graphs are two-colorable, namely those which don't contain odd cycles, right? So odd cycles are the obstructions, the real obstructions, but for some reason in this Hadwiger's conjecture, we exclude all cycles to obtain this two-colorability. In some sense, this seems too strong, and somehow this parity is not taken into account. And motivated by this problem, Gerards and Seymour looked at this minor variant where we also take some parity considerations into account, and this gives them some less restrictive excluded minor concept. Okay, but let me explain this. So first of all, let's go back to the definition of how I defined that the graph contains a kt minor. So we said to contain a kt minor, what I want to find in my graph is t disjoint so-called branch sets, so connected vertex subsets. And between any two of them, because it's a complete graph on t vertices, I will have at least one connecting edge. Now, of course, we can somehow minimize this picture because lots of the things are redundant, right? So if we just want to have a kt minor in a graph as small as possible, it makes no sense to draw more than one edge between the same pair of two branch sets. We can just kill all except one of them. So we can assume that in a sensible model of such a minor, we have only one edge between any pair. And also we can assume, because all we care about is connectivity of these vertex sets, that we take a spanning tree of all branch sets and then only keep the edges in the spanning tree, and the remaining edges we can also discard because this is still a connected subgraph. So if you have a KT minor, this also means you have this so-called thing called KT expansion, which is exactly what I've drawn here. So T vertices join trees, and between any pair exactly one edge. Now, this is useful to rephrase the minor notion this way, because then it's easier to define as odd minors. Odd minors, namely, somehow specialize this concept of a KT expansion a bit. So if you have a KT expansion, this is called an odd KT expansion if there's a certain two coloring of the vertices with some nice properties. So here's the definition. So the same as before, we have a KT expansion. And now we say that this is odd if we can assign one of two colors to each of the vertices in this expansion, in this case, red and green, in such a way that this coloring forms a proper coloring restricted to each of the branch sets. So each of these trees is simply properly colored. But then the important condition is that if you look at these connecting edges between different branch sets, these endpoints of them should always have the same colors. So these should be monochromatic, for example, green, green, red, red here, and so on. So this is the formal definition of this odd KT minor. And it's okay, it's a bit strange where this comes from and so on. But I think, okay, it's not very hard to see that in the small case where you have T equals 3, basically you can see that these minimal odd K3 minors are exactly odd cycles. So in some sense, this coloring and this in-between condition for the edges make sure that cycles which go through this minor have the parity we would kind of want from them. So for example, if you have an odd KT minor and you look at a cycle spanned by any three branch sets, which in the KT corresponded to a triangle, so to a cycle of odd size, then actually in this odd KT minor, it will still have odd size because it switches colors always except on the three edges which cross between the branch sets. So this is kind of the idea behind this definition. And again, there's this other definition by using contractions. Here you can say a graph contains an odd KT minor if you can obtain KT by first deleting some edges from G and some vertices, and then contracting a special set of edges. You cannot arbitrarily contract a set of edges. You need to contract the complete set of edges which lies in an edge cut of the graph. So you partition the vertex into two parts. In this case, you can see in this picture like the red and the green vertices, and then you contract all the edges which go between red and green, and you only keep those which have the same color set at endpoint. So if you do this here, if you contract a cut between red and green vertices, you will get exactly a K form. And so this is another way of saying it. Okay, so with this definition, I can give you the conjecture. So this is from 1995, and this conjecture simply says that actually graphs with large chromatic numbers, somehow generalizing this thing with bipartite graphs, the obstruction should have to do something with this odd parity, and therefore we expect that if a graph has chromatic number T, it actually also contains an odd KT minor, an odd KT expansion, and not only some arbitrary KT expansion. So this is the conjecture. Graphs with no odd KT minor, they can be T minus 1 colored. Okay, so now what is known about this strong conjecture? Obviously not more than about a normal Hadwiger conjecture, but yeah, let me look at some small cases. So T equals 1 is completely trivial. This is just empty graphs. T equals 2 as well. These are graphs which don't have edges, so let's not look at this. So T equals 3 is what I said. This is basically the motivation for this definition. So K3 minor free graphs are only forests, but actually K3 odd minor free graphs include all the bipartite graphs. So here somehow this conjecture is tight. It includes all graphs which can be two-colored. Now the next case, we don't have this anymore, but we still get a much richer class than for Hadwiger's conjecture. So K4 minor free graphs are series parallel graphs, which are a very simple class of graphs built in a simple way recursively, while the odd K4 minor free graphs have also a structural exact characterization obtained by Lovas, Schreiber, Trümpe, and Seymour somewhere in 1980. But this is, I mean, it's understood, but this is actually very complicated. And as far as I know, it's not really written down. So I read this in the survey article by Seymour. But okay, what is still known is that also the Hadwiger's conjecture holds for odd K4 minor free graphs. This was proved by Catlin in 1979. And then the next case, now it gets difficult because if we want to prove that odd K5 minor free graphs are four-colorable, this of course must be actually even a stronger statement than the four-color theorem. So there should be some trickiness in it. And in 2005, in a workshop in Oberwolfach, Genin announced that he solved this problem. But as far as I know, this has not been written up, and I'm not sure about the status of this result, whether it's now confirmed or still open. So yeah, and starting from 6, we don't know whether the conjecture is true, and we also have no idea, no clue about the structure either of K6 minor free graphs or K6 odd minor free graphs. So there the structure gets completely lost, and we don't know whether the conjecture is true. So unsurprisingly, this is not easier than Hadwiger's conjecture, and we don't know a lot for small values. And again, maybe it makes more sense first to look at some asymptotic versions. So let me say what is known for the asymptotic versions. So first thing you observe is that in contrast to what I told you before for the KT minor free graphs, where we had this very first bound by Kostoschka and Thomason with the degeneracy coloring, where we remove vertices of small degree, this whole approach fails completely for the odd KT minor free graphs, because, for example, bipartite graphs, of course, like K and N gets big, they are arbitrarily dense, but still they are bipartite, so they don't have an odd K free minor. So you cannot find any small degree vertices to color. You need to find a way of coloring. I mean, for bipartite graphs, it's obvious how you do it, but somehow you need to combine these ideas of coloring bipartite graphs with this degeneracy approach in a sensible way. And you need to find some new ideas. And so, I mean, at first, maybe it's not even obvious that some bound exists for this chromatic number, but Gielen and Huyen proved this in 2002 with some standard BFS layering argument. You can get an exponential upper bound for this chromatic number. And then finally in 2009, this large group of authors, starting with Gielen, proved an upper bound of O of t times square root of t, so mimicking this Kostoschka-Thomason bound, but of course it cannot be exactly the same proof for the reason I gave you above. But somewhere in the proof, of course, this result is used. So the proof basically considers different cases. It first constructs a large KT minor, which is kind of bipartite, which does not give you the oddness you want. And then around this, you build some additional paths, which somehow are supposed to break the parity to get this oddness inside the minor. I mean, this is very intuitive, but like I will not go into details, but it's a bit involved, this proof. Okay, so this was known until 2009. And then very recently, and now I will also give the recent developments concerning Hadwiger's conjecture, some new results have been obtained. So this is basically like a small timeline of asymptotic bounds for Hadwiger's and odd Hadwiger's conjecture. So the first couple of results I think I already mentioned. But then in 2019, Noreen, Postel, and Song, they had this big breakthrough that actually you can do better for the coloring than only using vertices of small degree. You can get the log t to the 1/4. So 1/4 instead of 1/2 in the exponent times t. And then actually later, Noreen and Song also wrote a paper where they took the same approach, but somehow modified it for odd minors and had some arguments, and they proved the same bound also holds for the odd Hadwiger's conjecture. And then in 2020, further breakthroughs by Postel. I mean, now the best bound is t times poly log t. So now it's not anymore logarithmic, but basically this exponent on top of the log t can be arbitrarily small. So it's t times log t to the 6. And this was also proven to hold for the odd Hadwiger's conjecture in another paper by him. And then now what is best known is t times log t, which basically just removes this exponent of 6. And I could also prove the same bound for the odd Hadwiger's conjecture. This is the result I will now show you in the next slides. I mean, I think if you look at this, you might think, yeah, okay, who really cares about these exponents of 6? And I kind of agree with you. So this is actually not the point of my results. What the point of my result is something much nicer, I think. And this, I think you can nicely see by looking at this table. I mean, it seems like it always was like this. Someone proved a bound for Hadwiger's conjecture, and a couple of years after, people with some additional work for odd minors and some other arguments, they proved exactly the same asymptotic bound for the odd Hadwiger's conjecture. And I mean, if you look at this, maybe you notice that this might not be a coincidence, right? So maybe there is some kind of a relation, and this is actually my result. So my result simply says the asymptotic of Hadwiger and odd Hadwiger's conjecture is the same. And if you can, this is now the thing on the next slide, you have this Theorem One, which says if you have any asymptotic function f of t, such that KT minor free graphs can be properly f of t colored, then odd KT minor free graphs can be 2 times f of t colored. So this is what I call asymptotic equivalence of these conjectures, because basically what this result implies is that you shouldn't, asymptotically at least, you shouldn't look at odd Hadwiger's conjecture anymore, because any progress you make there, you also have to do for the Hadwiger's conjecture, and any progress you do for Hadwiger also will give you something here. So basically this shows that all these previous independent results, which always were proven with different and new ideas for the odd minors, this is all not, this can all be reduced with this theorem. And actually, what is much nicer even about the theorem is that I think my proof is maybe the most simple proof of any of these asymptotic bounds given in this table, because it's a very simple reduction. This I will show you in the next slides, how you can obtain a bound on the chromatic number of odd KT-3 graphs coming from the KT-3 graphs. And yes, that's what I will show you now. So how does the proof of Theorem One go? So it basically all relies on a very, very simple lemma, which anyone probably could prove if you put it on an exercise sheet at your university. But yeah, it seems to be still kind of powerful. So this is what it says. So you give me any graph G, no condition whatsoever, and then I can always partition the vertex set of this graph into some number n of vertex disjoint subsets of the vertex set, such that they all induce bipartite and connected subgraphs. So in the simplest case, such a partition could be just consisting of single vertices. Single vertices are always bipartite and connected, but I mean, it can be more complicated. And the second condition is an interesting one. So the second condition says, now when you look at into the sequence of subsets, and you look at some xi and xj in the sequence with I less than j, then they have the following nice property. So whenever there's at least one, so either these two sets, xi and xj, don't have any connecting edges, they're completely separate in a graph, not connected to each other. But if there is at least one connecting edge between them, then there must also exist this kind of configuration here. Let me call this a fork in the following. So fork basically consists of one vertex in the right bubble. So this is the vertex V. And then it has two different neighbors. One on the, so A and B is the bipartition of this connected subgraph induced by xi. And then V has a neighbor both in the, let's say, green and in the pink side of this bipartition of the subgraph. And because this is a bipartite graph, this bipartition is also unique up to switching A and B. So this is a well-defined thing. Okay, so this is basically my lemma, which says, yeah, you can always find this partition such that either no connections or always at least two connections, and these connections go from the same vertex to two different sides of this bipartition of the left bubble. Okay, there's a very simple proof of this. So how do we prove this? So you just define xi basically greedily as follows. So you, let's say you have already defined x1 up to xi minus 1. Now for choosing the next step, unless you already covered everything, you just pick an inclusion-wise maximal subset of vertices disjoint from what you have picked so far, which induces a bipartite and connected subgraph, exactly what we want by the first item. And I claim this simply does it. So in each step, you simply pick a largest set disjoint from the previous sets, which satisfies this first condition. It always exists because, as I had, you could in the worst case always pick a single vertex if this is the largest thing. And yeah, I claim this also satisfies the second property. Okay, so why does it? It's a very simple reason. So suppose I have here my xi constructed early in the sequence, then xj constructed later in the sequence, and there's at least one connecting edge between them. If there's no, then we are happy. So let's say there's some connecting edge from some vertex u to some vertex v, and let's say u is on the green side of xi. Now, we said xi is a largest subset which is induces something connected and bipartite disjoint from the previous picked sets. So there was a reason that we could not add in V into xi and still be bipartite and connected, right? But if V does not have any neighbor in V, then we could have done it, because then we could have simply colored V also with pink. We could have put it into B and join it into this set xi. It would still be a bipartite subgraph. It will still be connected because you have this connection from V to U. So this is simply by this inclusion-wise maximality impossible. So we must also have an edge to a vertex in B. So we get this fork. This is exactly the claim I had. So that's the whole proof of the lemma. By this maximality of the left set, I could not add in V, so it must have had neighbors on both sides of the bipartition. Okay, so now with this lemma, actually the proof will be rather simple. So here's how it goes. So you give me any given graph.
Raphael,
yes.
You have alternative there. It's because of the connectivity that you enforce, right, on this xi sets, right?
Mm-hmm.
So okay, sorry, I got it.
Oh, okay, sorry. Yeah. Okay. So, any other questions to this lemma? Because I think this is kind of central. I will use the same idea also later. Okay. So now here's how this reduction goes, right? So you give me now a graph G for some number T, which is odd KT-3, and I will apply to it this lemma. Okay, so this is my graph G. I can decompose it into the subset x1 up to xn, which have these properties I said. And now we will construct another graph H from this, where we simply put one vertex for each xi, and we put a connecting edge between two of these corresponding vertices if there was a connection between the corresponding subsets xi and xj. So basically, we just contract these xi into single vertices, and this gives us a graph H, which has now n different vertices. Okay, and now a very simple observation is that if we can color the graph H with a certain number of colors, k, let's say, then I can color G with 2 times k colors. Because, okay, I mean, by definition, each of these xi is a bipartite set. It can be 2 colored. So all I need to do is basically take a product coloring of this k coloring of H and the individual 2 colorings of these sets xi. And because I contract the thing, so I keep somehow track of which xi did have connections in between and which didn't, this is still a proper coloring if I put this together. So the chromatic number of G is at most 2 times the chromatic number of H. And of course, what I will now do is to prove that H is kt minus 3. Then we are done, because if f of t is a function such that kt minus 3 graphs are f of t colorable, then okay, this inequality chain implies G is 2 times f of t colorable. Okay, so this is the main step we have to do. Prove that given that G is odd kt minus 3, this reduced graph H is kt minus 3. Okay, now I will do a proof by picture. So let's do t equals 4 and suppose towards a contradiction H contains a k4 minor. And now I will construct you a k4 odd minor in the whole graph G. So on the left we have H, on the right hand side we have G. And from this normal minor without this oddness condition in H, I will give you an odd k4 minor with all these colorings and so on in G. Okay, so I have just picked some example of a k4 expansion in H. So we have all these trees as the branch sets, and between any pair of them exactly one edge. So this is somewhere contained in H. And now I blow up each of these single vertices in H to their corresponding xi sets, to corresponding sets in my partition, right? Each of them itself corresponded to some subset of vertices in G, which induces a bipartite and connected subgraph. So I expand this picture, then I get the thing on the right. And what I know is that, I mean, whenever I have an edge and H, between the corresponding bubbles here, I have some connection. And also because these bubbles here are all connected sets, I can, of course, always pick a spanning tree of them and pick a proper coloring of the spanning tree. This I can simply do. This is what I do here in this picture. So I take a spanning tree of each of these sets, x1, x2, and so on, to color it properly. And there's also a proper 2 coloring of the corresponding subgraph because it's bipartite, right? So the bipartition is unique. It's a connected graph. So the bipartition of the spanning tree and the graph is the same thing. Okay, so I do this, and now I put this coloring simply together. This gives me now the 2 coloring of our vertices. And now all I have to do is fill in the in-between edges, which I now didn't yet show in the picture, so which go between these bubbles. And I will do it in such a way that it gives me an odd k4 minor. So what do I have to do for this to work out? So what I have to do for this to work out is I need to connect up the bubbles inside one big bubble in such a way that it still forms a proper coloring of the whole subtree, which will then arise here. But for the connections between the big bubbles, I want to be monochromatic. These are the conditions I have for the odd minor. And I will achieve this with this extra condition I have on this sets xi and xj. For example, let me give a very simple example. The set x1 here and the set x12, according to the picture on the left, they have at least one connecting edge. Which means that if I look at x12 compared to x1, there was this kind of fork. There is a vertex in x12 which has both a neighbor which is pink and a neighbor which is green in x1. And same goes for every pair. If I look at x12 and x13, then there is a vertex in x13 which has both a neighbor which is pink and a neighbor which is green in x12. This is the condition I have on these sets. Okay, so let me draw this picture as an example. It looks like this, right? For every connection in H, I get one such fork. And basically the direction of this fork now doesn't really matter, because what matters is that I can choose for each of the connections now whether I want it monochromatic or bichromatic. Because I have this fork, always one neighbor will be of its color and the other neighbor will be of distinct color. So I can simply select edges inside these big bubbles so that they are bichromatic, so that these form in total a tree with a proper coloring. And between the big sets, I can choose the monochromatic edges. So I can simply do this, and this is not minor, right? Because now I have a union of disjoint subtrees connected only by these edges, which are also in a tree-like pattern. So this is in total are 4 disjoint subtrees, all properly colored. And between any pair of them, I have a monochromatic edge. And that's an odd k4 minor. So this is basically the whole idea of the proof. If H was kt minus 3, then G was odd kt. No, sorry. If G was odd kt minus 3, then H was kt minus 3. And then with the product coloring, we are done. So this is the whole proof. Any questions so far for this? Okay, I hope it's clear. So yeah, let me just quickly summarize what this means. So this means, as I said, that all these bounds which were previously known for the chromatic number of KT minor free graphs always apply without any further thought to the odd KT minor free graphs. And for the asymptotics, somehow there's no big distinction anymore between these two topics. Okay, so now for the second part of this odd minor topic, I will talk about another result of mine, which is not about proper colorings. Now I switch to the so-called improper colorings. And this is also a widely studied kind of graph coloring. There's, for example, a nice 70-page survey by David Wood, different classes of graph coloring, which you can have a look into with some really nice summary of results. So what is the general idea of these improper colorings? So we have some nice class of graphs, which we would like to color with few colors. But sometimes maybe we don't actually care about the fact that we don't have any conflicts at all, right? We say a conflict is if two vertices which are adjacent have the same color. I mean, maybe we are happy if this happens sometimes, but not too often in some sense, right? So for example, if the structure of monochromatic subgraphs is simple enough, it could be that this is already good enough for our application, which we have in mind. So and there's two main variants of this kind of colorings which are studied, and they are called defective and clustered colorings. So let me just give this simple definition. So the first thing with defect D, so this is, we say that a K vertex coloring of a graph G, now this must not be proper, has defect D for some integer D if the maximum degree of all the monochromatic induced subgraphs, so if you look at, for example, the red vertices in the coloring and the induced subgraph, the maximum degree of the red subgraph is at most D, and the same for the blue and the green and so on. So all the monochromatic components or monochromatic subgraphs, they have bounded maximum degree by D. Then we say this is a coloring with defect D. And qualitatively stronger concept is the clustered colorings, where we say that we want a bounded clustering. So we want a K coloring, but now all the connected components of the induced subgraphs, which are monochromatic, should have all size at most C. So basically, we allow that some vertices of same color are connected to each other, but they shouldn't form large clusters of same color vertices. They should only be separated into small single components. So this is the goal when you do defective and clustered coloring. And in particular, this is interesting because you can study it from a qualitative kind of view. So usually, if we do graph coloring, we minimize the number of colors, and this we also do here as well. And then there's the secondary goal that, okay, you somehow want to also have small defect and small clustering. And for example, if you only look at one fixed graph G, I mean, this wouldn't make sense. But for one fixed graph G, I can just pick D and C so large that I always can color all vertices with the same color. So that's not the kind of thing this concept is aimed at. It's more for graph classes. For example, you could ask, can I always free color a planar graph such that all the monochromatic components have some bounded clustering, but not really care about how large this clustering is, just that it's bounded by some constant. And this is leads to this notion of the defective. This is this chi delta, and the clustered. This is this chi star chromatic numbers of classes of graphs. So if this calligraphic G is a class of graphs, for example, the defective chromatic number of G is the smallest number K, such that there exists some constant D, such that all graphs in a class can be K colored with a bounded defect, bounded by the constant D. And the same for the classic coloring. Okay, so this is the kind of problem we can look at. And in some sense, for many of these conjectures, such as for Hadwiger's conjecture, this gives you some nice relaxations to work on. For example, you could say, maybe we cannot prove Hadwiger's conjecture, but maybe we can prove this weaker variant for, let's say, defective coloring, that I can always color with T-1 colors, such that at least my monochromatic components have a bounded size depending only on T. And actually, these kind of variants of Hadwiger's conjecture have been also studied quite a bit. And now in the next slides, I will again have a brief summary of known results there. And it's actually a lot. I mean, I was actually surprised how much people have done at this. So let me give a very brief overview here. So you can see that the first bound for KT minor free graphs for defective and clustered coloring was by Kawabayashi and Moha. They proved that you can use a linear amount of colors. And note that this is something we don't know for the proper colorings. There we still need a superlinear amount of colors. So 31.5 times T, with some constant bound only depending on the clustering and the defects. By the way, whenever you get a bound on the clustering, of course, it also gives a bound on the maximum degree if you subtract 1, right? That's why I always write this. If I have a bound on the clustering, this also gives a bound for the defect. So this is somewhat a harder thing. And then, okay, the constant in this result was improved several times. And then for Edwards et al. In 2015 actually managed to get an optimal bound, which mimics Hadwiger's conjecture for the defective setting. So there they proved you can T-1 color as Hadwiger's conjecture desires KT-3 graphs with a bounded defect, but not yet with a bounded clustering. And actually, why is this tight? I mean, this is also not obvious, right? So now that we have this relaxed variant of coloring, it could be in theory that now we suddenly can use much fewer colors even, and we don't even have this natural lower bound of T-1, which is normally given by a complete graph on T-1 vertices, but now this doesn't work anymore. We need some infinite class of graphs as a construction in order to prove this lower bound. But in the same paper, Edwards et al. Also gave a very nice construction of KT-3 graphs, which indeed show that you need T-1 colors in general to color graphs, which are KT-3 with bounded clustering. Right? So in order to show that somehow this class of graphs needs that many colors, you cannot only draw one graph, because then you could always color it monochromatically. You need to draw an infinite sequence of graphs. Okay, so this is, I'm just saying this is still tight. So T-1 is still the best you can hope for. And then for the class of coloring, we don't know this tight result yet, but there have been lots of improvements, as you can see here. And the state of the art bound now is that you can do it with T+1 colors. This was proved very recently by Liu and Wood. So this is just too off from what is conjectured or is possible. And there was an announcement by Dvořák and Noreen a couple of years ago that they proved the T-1, the tight bound, but I think this has also not been written up yet. And actually, one comment also about this non-explicit things I write here. I always write C of T, which is just some function of T, right? That's what I mean is this just depends on T. And the reason I mostly don't write this is that it's usually not very explicit and very, very bad bounds. So many of these bounds depend on some constant and functions from the graph minus theorem, and we know that they are not very good, right? So they are sometimes power tower functions and so on. So we just keep this in this form, and if there are some reasonable bounds, then I will write them, but otherwise I just have this short notation. Okay, so this is the state of art for Hadwiger's conjecture with classic coloring. Now people have also looked at this for the stronger variant with the odd coloring. So Kawarabayashi in 2008 proved again a linear bound for 96 times T colors, but again with some graph minor-like function on the clustering and defects. And then the constant was improved a lot by Kang and to 6T-9 in the defective version, and for the clustered version it's a 10. And you can see that then very recently there was this slight improvement to 8 times T, and now I have a result which says you can actually do 2 times T-1. So this is within a factor of 2 of what you could do optimally. We still have the same lower bound of T-1, which would probably be optimal. And one difference I think which is also nice from my result is that I don't need this very bad functions from any kind of graph minor theorem or something like this, because my proof relies on a different method than those of previous authors. I have here explicit bound of T-2½ for the clustering. And my method is basically inspired by a very nice paper which appeared on the previous table by Van den Heuvel and Wood, who proved the same result for the KT-3 setting. And I managed to somehow extend their technique also for the odd KT-3 graphs. And of course, it remains open to prove the odd Hadwiger's conjecture as well as the Hadwiger's conjecture in this clustered settings. This is still not completely resolved. Okay, so let me also show you this proof. I think it's also nice. So this is the main result. So if a graph does not have an odd KT minor, then we can 2T minus 2 color the vertices, and all monochromatic components in this induced by this coloring are only of this size T-2½. And exactly the same result, only with the stronger condition that I don't have a KT minor, was proved by Van den Heuvel and Wood in 2018. And it seems so far it has been overlooked that somehow you can apply the same technique. And the other techniques by previous authors for this odd KT-3 graphs, they were very different from what I will show you now. Okay, so let me just go right into the proof, and I will use one black box result, which is not really hard to prove by Van den Heuvel and Wood. It's actually also probably an exercise. It's not very, it's a simple result, but it's very useful in the setting. So what does it say? So this first lemma by Van den Heuvel and Wood says the following: if you give me any connected graph G, and you fix a set of vertices S in this graph, you mark some vertices, let's say the number is K, then if I look at the smallest, or let's say minimal, induced and connected subgraph, which covers all these vertices. So I somehow want to basically connect these vertices in this graph by an induced subgraph, which I marked, and I want to do this with as few vertices as possible, then this graph has some nice properties. For example, among other properties which Van den Heuvel would prove, what matters for me now is that these graphs, these minimal graphs, minimal connectors, let's say, they can always be true colored with very small clustering, only k half, where k is the number of vertices I need to connect. And this is some simple inductive proof on the size of this. Okay, so this lemma I will use as a black box, and for my purpose, this is not good enough. So Van den Heuvel and Wood use this in order to prove their result for the KD minor free graphs. Now I will have a modification of this with some additional properties of this graph H, which will then help me later. So let me say what my modified lemma says and then how it's proved. So this modified lemma says that if you have a connected graph and this marked set of vertices S of size K, then maybe not a minimal, but there exists some induced and connected subgraph H, which connects the vertices in S. So now this is not necessarily very small anymore. I don't have the minimality condition anymore. But there exists some induced and connected subgraph connecting S, such that the following three properties are satisfied. So the first is the same as what Van den Heuvel and Wood say. So Van den Heuvel, I think, sorry. There always exists a partition of the vertex set into two parts A and B, such that they induce subgraphs with small connected components of size at most k half. This is just the same as saying two colorable with clustering k half. And the second and the third property are now new, and this is what is important for me. And you will not see the region set, but in the end, everything will make sense. So just be a bit patient. So the second property says that actually not only is my graph H in itself connected, but even if I only look at the edges which go between A and B, it's still connected. So if I look at the bipartite spinning subgraph of H connecting vertices in A to B, this is also still connected. And the third property says the following. This is actually very reminiscent of this previous lemma I had in the asymptotic equivalence proof, that if you have any vertex V in the graph G, which is not yet in this connector, then, but if it has a neighbor in the connector H, then it actually must have neighbors both in A and in B. Okay, so this is the third property of my graph. Any vertex from outside connected to it is not only connected to one side of the bipartition, sorry, it's not a bipartition, of the partition AB, but to both sides. Okay, so let me again show you how you get these two additional properties. And this is also a very simple proof, similarly optimizing. It's similar to the previous proof when I did this partition with x1, x2, and so on. So what we do is we already know by the Van den Heuvel and Wood result, there exists some minimal induced and connected subgraph which contains all of S and which can be true colored with bounded clustering at most k half. Okay, one such graph exists, but it does not necessarily have these nice properties 2 and 3. So how do we get them? We look at all possible triples H, so connected induced subgraph containing A, S, and a partition of its vertex set into parts A and B. So among all these triples, we pick one. Sorry, and it also has this nice property that it can be true colored with bounded component size. So A and B have no large components. So among all these triples, which are guaranteed by Van den Heuvel and Wood, basically, I pick one which maximizes the number of edges spanned between A and B. So maximizes the number of cross edges between A and B. Okay, and I will claim that if I get such a triple, then it will have all the two other properties. Okay, so the first property said that if I look only at the edges going between A and B in H, then this should be a connected graph still. Okay, so let's prove this. Suppose that this optimal triple does not have this property. So if this bipartite graph is not connected, then I can partition its vertex set into X and Y, two disjoint parts, X and Y, such that there's no connecting edges in this bipartite subgraph defined by A and B, right? So as you can see in the picture, this basically means that you don't have an edge going from X intersect A to Y intersect B, or from X intersect B to Y intersect A. So in general, the graph is still connected, which means, okay, there are still some edges between, for example, X cap A and Y cap A, so that the graph overall is connected. But in the bipartite part of this graph, this bipartite subgraph going between top and bottom, for this it's actually a disconnected partition. For this, we don't have edges. Okay, so suppose we had this would be the case. This bipartite subgraph is not connected. Then actually what we can do is simply we switch on the right-hand side these two sets. So we switch Y cap A and Y cap B with each other, and just don't change the graph H, but change A and B in this way. So we change the coloring in some sense. And if we do this, what happens? So basically now this non-edges which go across here, now they become horizontal, and this one existing cross edge between X cap A and Y cap A now crosses, right? So basically the picture now after exchanging Y cap A and Y cap B looks like this. And I claim that H with this new partition is better than the previous triple. Okay, so why? So first of all, let's see why it still has all properties. So of course the graph H didn't change, it still contains S and so on. But also I didn't increase my component size, right? Because if I look at only the green part, for example, every connected component in the green part, because there's no connections between x cap A and y cap B, is either completely contained in A, and therefore at most as large as a component of A, so at most k-half, or it's contained in a component of B, and then it's at most k-half as well. And the same argument on the bottom side. So this is still satisfied because of this disconnection. I can somehow switch and I still preserve my class of coloring. And also now I added one new edge which goes across, right? Because previously I did not have any crossing edges from left and right side going between green and pink, but now I have this one new connecting edge which goes between green and pink. And so this means I have more edges going across. So this is a better triple, and this contradicts. So my bipartite subgraph must have been connected. This is the first property. Otherwise, I can always, if I find components, I can always do the switching, and I will get more edges across. Now the second proof is very similar as well. So for the third property, I said, now let's look at this optimal subgraph H with the partition A and B. Suppose that there is a vertex outside which is connected to some vertices in H, but not to both parts A and B. And there are exactly the same reason works why this makes no sense. Because in this case, you could just add in V to H, get a larger induced and connected subgraph, which also still includes S, and you color it green, and then you don't change anything about the property that this is a classical coloring, right? Because V is not connected to anything in A by assumption. So V itself forms a connected component of the induced subgraph of this new green set. And for P, nothing changes. So this new triple we get is better than the previous one. And again, a contradiction. So if a vertex outside my H has neighbors somewhere inside, it must connect to both A and B. Okay, so these are two nice properties, and they will be later very useful. I mean, you can already imagine that somehow just connecting to both things will be very useful in constructing the odd minus later on in a very similar way to my previous proof. Okay, so now here comes the main result, which will imply the colorability result. And this looks very complicated, but I will go through it, and it's actually not that complicated. It's what Van den Heuvel would call the decomposition theorem. So basically what it says that if you give me any connected graph, which is odd KT minor 3, I can partition it into nicely structured disjoint subgraphs, which are connected and have have a nice structure in relation to each other. Okay, so let me specify this. So if you have any such graph, there exists some finite number L, such that I can partition basically my vertex set into L distinct parts, each of them inducing one of these disjoint and connected subgraph H1, H2, and so on, up to HL. And they have very nice properties as follows. So the first one is simply the same as I basically got from this lemma. So it simply says that every one of these disjoint subgraphs can be two-colored with bounded clustering, at most T minus 2/2. This is what I want to get in the end anyways. So each HI can be partitioned into two parts AI and BI, such that they induce connected subgraphs, induce subgraphs with no large components, at most T minus 2/2. Okay, this is what we will basically get from this lemma. And also the second property is inherited from the lemma. It says that if I look at the bipartite subgraph span between the AI part and the BI part of HI, this is also connected. Now, the third and fourth property are interesting. So 3 is a generalization of the last property from the lemma. It says basically that if you give me any vertex V, which is not contained in the first I subgraphs H1 up to HI, but it is connected to HI somehow, to some vertex in HI, then it also has neighbors in both the A part and the B part of HI. Okay, this also comes from the lemma. And the fourth invariant or property is actually maybe the most important one. So this says that if you have any connected component of the graph after removing the first I sets, then if you look at to which sets from among the first I it is connected, these form a clique basically. So these, if you look at any component of the graph contained in HI plus 1, HI plus 2, and so on, and you look at to which among H1 up to HI is it adjacent by an edge, then these are also pairwise connected to each other by edges. And they are at most T minus 2 of them. Now, this I know sounds all very technical, but actually all we need from this theorem once it is proved. So all these technical conditions I list here are only useful for the proof, but actually from what we need from it in the end to get the coloring result, only the fourth property is important. And I will now, before giving you the proof of this theorem, tell you how I get from the fourth property that my coloring result is true. Okay, so for instance, I mean, yes. So what does this for in particular mean is that if I, for example, look at HI plus 1, I mean, it's a connected subgraph of this graph G minus V of H1 up to V of Hi. So it's contained in one connected component C like this. So if I look at its neighboring subgraphs to the left, basically my sequence, then these are pairwise adjacent and at most T minus 2 of them. So this somehow screams for a degeneracy ordering, right? So I mean, in a degeneracy ordering of a graph is basically exactly the same thing. If you look at the I+1 vertex and you look at its neighbors among V1 up to Vi, if there are at most a constant number of them, this means their graph is degenerate. So this is actually exactly what we will do here. If we do the same auxiliary graph thing I did in the previous proof and contract all these HIs, then I will get a T minus 2 degenerate graph from this condition. Okay, so let me just do this in the next slide. So here I've written again these important properties. So I get a partition of my graph into H1 up to HL, each of them 2 colorable with clustering T minus 2 half. And if I contract all these HI into single vertices, this graph becomes T minus 2 degenerate. Because if I look from any HI to the previous HJ, which with smaller j, I'm adjacent to at most T minus 2 of them by the fourth invariant. Now, this immediately basically yields my theorem, because a graph which is T minus 2 degenerate, I can greedily color with T minus 1 colors. So then I again can do this product coloring, the same thing I did before. I have these T minus 1 colors for my small graph. Now I expand it with this proper 2 colorings of these HI, and sorry, with this 2 colorings of the HI which have bounded clustering, which in total give me a 2 times T minus 1 product coloring with the same bounded clustering. Because if we do this proper coloring, no monochromatic components can be merged between different HI, basically. Okay, so this is a very simple reason why this decomposition result yields the colorability. But now, of course, we want to see the proof of this. And it's actually not as bad as you expect. And I will now go over to pictures. I think pictures always make things better. But still, let me say one general thing how I do this now. Right, so all these conditions basically only refer to this subgraph HI in some sense. They say first property says HI has this nice partition. Second property says this nice partition induces some bipartite connected subgraph. Third property says for every vertex outside the first I subgraphs, which is connected to HI, again, references to HI, I have neighbors in both sets, A and B. And the fourth property also refers somehow to these connect components after deleting your first I set. So somehow this can be indexed by I. If I prove somehow that these properties hold for every I from 1 up to L, then I also have proved it in general. And what I want to say actually is that we can construct these subgraphs one by one. So if I have constructed H1, H2, and H3, and now I want to construct the next subgraph, then all I need to care is that I satisfy the new invariants which come from the H4. And all the previous ones, they remain satisfied when I add a new subgraph. This is all I want to say there. You don't need to worry about interaction of the invariants. When you add a new subgraph, all you need to do is care about the invariants caused by it. Okay, so let's start. Let's first define the first subgraph. So H1 will actually do the similar thing to what we did in our first proof. H1 will be a largest induced and connected and bipartite subgraph of G. Right? In the worst case, it's a single word, it's a single edge, for example, or something like this. But it could also be larger. And then it gives us naturally the sets A1 and B1 because these are simply the color classes of the bipartition of this graph. So this is how we pick H1. And yeah, I mean, now the invariants actually hold very easily. Let me quickly say why. So this first invariant simply says I have this coloring with bounded clustering. I mean, here I have clustering 1 because these are isolated vertices in A1 and B1. So this is, of course, true. Why is this bipartite spinning subgraph connected? I mean, because in this case, the bipartite spinning subgraph of HI at H1 between A and B is the same as H1. So H1 is connected, so this thing is also connected. The third invariant, third invariant follows from the maximality of H1 with the same idea. So if you have a vertex outside which connects to H1, then it cannot connect only to A1 or B1 because otherwise you could join it in. Same as before. This is the third invariant. And the fourth invariant says if you have any connected component of the graph after removing H1, then it sees at most T minus 2 neighbors among the previous subgraphs. I mean, there's only one here, which could be a neighbor, so this is also trivially satisfied. And it says that the neighbors form a clique, but you have also only one thing constructed so far, so this is also trivially satisfied. So either empty or one vertex, basically. Okay, so this is just, I mean, very simple base case. Now let me go to the more interesting case. Let's say I constructed H1 up to HI, and let's, for example, say I equals 4 for this example. And now I want to construct H5 with this new, satisfying all the invariants 1 up to 4 still. Okay, so how I will do this is that I will look at the graph obtained by removing what I've constructed so far. So this is on the right-hand side, G minus the first subgraphs. And inside this, I have some connected components. This is not necessarily a connected graph anymore. It splits into some connected components, and I just arbitrarily select one of them. Let's call it C. Really doesn't matter which one I pick. Okay, let's pick a connected component of this rest. And now I want to find H5 in there. And now the lemma can shine, because what we will do is the following. So first we will say, C, please tell us to which of the previous subgraphs are you adjacent? To which of them do you have an edge? And by our fourth invariant, which already holds, we know that this is these subgraphs are at most t minus 2, and they are pairwise adjacent. And in this example, let's say I pick t equals 5, just to make the numbers make sense. So t equals 5, C is adjacent to at most 3 previous subgraphs, and they are pairwise adjacent. So for example, C could be adjacent to H2, H3, H4, but then they also must pairwise have at least one connecting edge in between. Okay, this is what we know by the invariant. And now I just select for each of these previous neighbors, H2, H3, H4, one vertex which connects to it. So V1, V2, V3. So this is a set of at most t minus 2 in general such vertices. And this would be now I focus on this component C and apply my lemma to it. C is a connected subgraph. It has this subset of at most t minus 2 vertices. So my lemma guarantees me that there's a nicely structured subgraph H, which is induced and connected, includes all those vertices, and has all these other nice properties. So let me say this again. So if S is my set of these connection vertices to these previous neighbors, in the connected graph induced by the component, by my lemma, I have a subgraph H of this component, which is induced and connected, includes all the VI, is two-colorable with clustering at most t minus 2 half, because k half is in this case t minus 2 half. K is the number of vertices I select here, and this is I have at most t minus 2 previous neighbors. And also, I have this other two nice properties, that this bipartite subgraph induced by the 2 color classes of this classical coloring is connected. And if I have a vertex in the component outside my subgraph H, which connects to it, then it must see both sides, A and B. Okay, so this is now makes it obvious how I will define H5. H5 will simply be H, and A5 and B5 will simply be the A and B from this, coming from this lemma. Okay, so inside this component C, I now found my H5, which includes all those connections to previous sets, and has this classical coloring with A5 and B5, which still satisfies all the invariants I want in my decomposition theorem. Because let's go through this one by one. The first invariant simply says I have this classical coloring. Yes, I have this because of my lemma. Okay. Second invariant says bipartite subgraph between A5 and B5 is connected. Yes, I have this by my lemma. Okay. The third invariant, and now it gets more interesting, says every vertex which is not among the first 5 subgraphs I already constructed, if it connects to H5, then it must connect to both A5 and B5. But this is also trivial here, because, okay, where can such a vertex be? It's either outside C, but then if it's outside C, of course, it's not connected to any vertex in H5, because it's not even connected to C, right? It's a component. Okay, so then we don't need to worry about this condition because it's empty. And if V is inside C, then we get it again from the lemma that if V has a connection in H, then it actually needs to see also B, A and B. Okay, so the third invariant is also simple from the lemma. And the last invariant says that if I now, and now it gets a bit tricky, now I have to maintain this nice invariant for the components which are in what remains. Okay, so the fourth invariant says for every component which is in the contained of the graph obtained after removing H1 up to H5, if I look at what it sees among the so far constructed things, these are pairwise adjacent and at most t minus 2 many. And this is actually where the real crux of the proof now lies, and where I will construct, where I will use the property that I'm odd k t minus 3. Okay, so where could in this picture a component C prime, now let's call it, of the graph after removing H1 up to H5 sit? Where could it sit? I mean, if you look at this picture, simply either it's included in C or it's in one of the components on the right hand side here, right? I mean, it cannot be somehow intersecting C on the boundary, because then C would be larger. So C prime is either here, but then there's a property I said holds by the invariant, because by the invariant, in this case, C prime is already a component of the graph after removing H1 up to H4, and it is not connected to H5 at all. So we just know by the induction hypothesis, by the invariant which we already have for these components, that it's connected only to some subset of H1 up to H4, and that these things to which it is connected are not many and are pairwise adjacent. This is from the previous invariant. There nothing interesting happens. Interesting is if C prime is inside C somewhere, because now it becomes possible that it gets a new connection to this new subgraph H5. And now we need to rule out that one bad thing happens, because, okay, to which things could the C prime in principle be connected, right? By assumption, H2, H3, and H4 are the only connections of the bigger component C outside. So definitely C prime has only connections to H2, H3, H4 at most, maybe not to all of them, to a subset of them, and maybe to H5, right? So C prime has connections to a subset of H2, H3, H4, H5, which are already pairwise adjacent by the way we constructed it. So we don't need to worry about this part. All we need to worry about is that now, because we add one new neighbor, H5 maybe, we go above the T-2 threshold of how many previous sets we can be connected. So the only bad case is basically if we previously were already tight. So if previously C prime was already connected to both H2, H3, H4, and now additionally it gets connected to H5, and we are above what we want, right? We want at most T-2 previous neighbors. So if somehow these are T-2 sets here, and we get one additional neighbor, this is bad. So the bad picture looks like this. C prime is connected to all the things C was connected to, right? H2, H3, H4, and also to the subgraph H5, and now it has too many neighbors, namely 4 to the left, which is more than T-2 equals 3, what we want in this example. Okay, so we get all these connections, and you can already see this is basically already a complete minor, but this, I mean, this is where the proof would stop for KT minors, but we have to make it an odd KT minor. And for this, that's the reason why we carried all these additional strange invariants, right? And now we will do a construction of an odd K5 minor, which will give a contradiction and which will show that this bad case will never happen in our construction process. Okay. By the way, sorry for this picture. I don't know how this happened, but I couldn't fix it. So this is just pink. There's nothing special about these color dots. So this is the same picture again, but it's a bit more complicated. So what changed? I applied my invariant because let's, for example, look at one connection here from this vertex in A2 to this vertex in A3, right? This right-hand side vertex in H3 was not included in any of the previous subgraphs. So my third invariant says that if it has a neighbor in H2, it also must have a neighbor in V2. And this is true for all the other connections as well. So I again get these kind of forks. For every connection, pairwise connection between two of these bubbles which I have here, I will not only get this connection, but I will actually get a fork where I have a vertex at the right-hand side, which connects both to the upper and the lower half of the left-hand side, basically. And I mean, this now gets very complicated to draw, but I think you see what I mean, right? For example, if I have this connecting edge, it's connected, it's a vertex not in the previous, not in H1 up to H3, which connects to H3, so it must also connect to B3. Okay, so I have some additional edges which I get from this, and I can draw these in this picture. So between every pair of some Hi and Hj, where I is less than j, there's a vertex in Hj which has neighbors on both sides of Hi. And these are exactly T different sets. So now it's just easy to get this odd KT minor by applying the remaining invariants. So what we will do is, we know that for each of these 4 bubbles here on the left-hand side, I have a spanning tree which only uses cross edges, only goes between green and pink edges, vertices. Why? Because I can not only look at this subgraph H2, which is connected, but also at this bipartite subgraph obtained by looking at the edges between green and pink. And our invariant said this is also always connected. So this is also connected. I can also of this pick a particular spanning tree which only alternates between green and pink. So I can do this for all these 4 things on the left. And for C prime, I don't have this, but for C prime, I can just pick some spanning tree because C prime is a connected component. It will have some spanning tree. So pick something and take a proper 2 coloring of the spanning tree as well with green and pink. Now this gives me my coloring of the vertices, all right? So for the things, first 4 things here, I just pick the color from depending on which side it is on. And for C prime, I take this proper coloring of the tree. And we do the same thing as before. We can select the right in between edges, right? So inside, so this will give me my odd KT expansion. I have this disjoint T, disjoint trees, all properly colored. And because I have these forks between any pair of 2 such trees, I can always select a monochromatic edge. Because I always have either the option to get a monochromatic or dichromatic edge. So I can select those, and this gives me the odd K5 expansion, or in general, the odd KT expansion. So this is a contradiction. I cannot have this. That's why this bad case in my construction where I get above the threshold of T-2 neighbors on the left side will never occur, and my iterative construction of these subgraphs will pass through until I have covered all the vertices. So this is the proof of this decomposition theorem, and I told you how to get from this 2 times T-1 coloring by the product idea, and so that's it. That's the proof of my result. Okay, let me take a look at the time. Yes. So I already asked Piotr when he asked me to give this talk whether there's really so much time for it. And I'm sorry, but I have to say that there's still a second part of this talk. I mean, let's see how far I get. But it's about a related topic, and I think there's some nice results. And at least I want to tell you about the results. Let's see about the proof. Okay, so please wake up if you got lost previously. A new topic, and you can understand it again. Okay, so part 2, list colorings. This is about the so-called list Hadwiger conjecture. So odd Hadwiger, list Hadwiger. You see there are lots of variants of these. But I think it makes sense because there's a very natural question lying beneath this, basically, which is, does Hadwiger conjecture carry over also to the list setting? Okay, so what do we mean with this? So I mean, I guess most of you know it, but still let me repeat this definition. So given a graph G, for list coloring, we always have to set up that every vertex gets assigned a list of colors. And in contrary to the normal graph coloring, now not every vertex must have the same possible palette of colors. Different vertices can have different set of colors from which they can pick their color for the proper coloring. So this is exactly the definition. So if you have for every vertex V the set L of V of available colors, then an L coloring is just a proper coloring where every vertex chooses from its list L of V of colors. And now to be K list colorable or K choosable, we mean that no matter how you give me an assignment of lists, each of size at least K, but possibly very different, I can pick from these lists. I'm list colorable. So the list chromatic number denoted by the subscript L, chi L of G, is the smallest number K such that you're K choosable. Okay, and I mean it's clear that you can also select always this list of colors from 1 up to K, for example. Then this is just a normal graph coloring. So list coloring is definitely not easier than graph coloring. But at first sight, it's not obvious why it's actually harder, because you would think, I mean, different color lists, I mean, should make it somehow easier. I mean, we anyways like different colors, right? We want to have different colors at endpoints. So it's kind of intuitive that why should it be so much harder? But there's a significant difference between these parameters for certain graphs. So for example, for bipartite graphs, complete graphs K and N, it is known that this chi L can be arbitrarily large. K and N has a list chromatic number roughly theta of log n. So they can be arbitrarily large even on graphs which are 2 colorable. So this makes it more difficult sometimes. But still, for some settings, it makes sense to ask whether somehow this extension from the normal graph coloring to the list coloring could work or does make sense. And Borowiecki, in this case, 1993, asked this question for Hadwiger's conjecture. So he asked, is KT minus 3, does this always imply that the graph is T minus 1 list colorable? Obviously, we cannot do better than that because of Hadwiger's conjecture, but maybe even this is true. But yeah, I mean, you can go through the small values of T. For example, for K4 minus 3 graphs, it still works because I told you previously, these graphs are series parallel. They are 2 degenerate. So you can actually, so this degeneracy coloring also works for this, right? If you have a vertex of degree only 2 and you remove it, you list color the rest, and you insert it again, then you have, let's say you have 3 available colors in your list, you can insert it again. And I mean, you can pick one of the 3 colors which does not appear in the neighborhood. You have enough choices. So this degeneracy idea still works for K4 minus 3 graphs, but for the K5 minus 3 graphs, the degeneracy is not good enough. You have only vertices of degree 5, which would give you 6 choosability, which is not good enough for the Borowiecki question. And actually, it is not even true. So the first construction of graphs which are planar even, so in particular K5 minus 3, and are not for choosable, was by Voigt in 1993. I mean, these graphs are actually rather large, and still I think no very, very small constructions are known for this, like maybe 80 vertices or something like this is the smallest, if I'm not mistaken, but I could be wrong. But there are constructions of planar graphs which cannot end a list assignment with 4 colors per list, which are not choosable. So this extension already breaks for T equals 5. So you could say, yeah, I mean, this makes no sense. But people went further and asked, okay, but what is the truth? Right? What bound can we guarantee on the list chromatic number if we are KT minus 3? And of course, planar graphs are the most interesting. So Thomas in 1994 proved the conjecture by Erdős and others that planar graphs are actually 5 choosable. And I mean, if you haven't seen this proof anywhere, Google this paper by Thomas and look up the proof. It's the nicest proof I've ever seen in graph coloring. This is so elegant. Yeah, you just have to look it up. There's also a nice proof of this that it still holds in the K5 minus 3 setting, which is not a completely trivial extension by Shrikovsky from 1998. So this also works. So we cannot always give an upper bound of 4 for the quadratic number as for the quadratic number, but one more color suffices for K5 minus 3 graphs. And now for larger values of T, if we think about asymptotic bounds again, we can, as I said, use again this degeneracy coloring approach by Kosushka and Thomason, which also works for this coloring, and then you get T times square root of T as an upper bound. But these improvements for this asymptotic bound for the chromatic number have also been done for this colorings by Postel, for example, 2020. He proved that you get also this T times log T to the 6 for this colorings, which I think is now the best which has appeared. But again, maybe the exponent is a bit smaller, but I think something of this order of magnitude. Right. So what we believe is true, or what people have conjectured to be true, Kawarabayashi and Muha in 2007 said, okay, I mean, maybe it's not T minus 1, but it should be a linear bound in T for sure, right? So there should exist a constant C, at least one, such that KT minus 3 graphs are C times T list colorable. And actually, you could even go further, because Wood said in 2010, yeah, but okay, for planar graphs, we need only one additional color. So why not? Maybe it's always works with T colors, right? I mean, let's hope. Let's be positive. So this was from 2010, this conjecture, but then actually it turned out that not even this adding one color is somehow not sufficient to go from normal coloring to this coloring. So Barat, Jouré, and Wood in 2011 found a very nice construction of graphs, which generalized basically this result for the K5 minus 3 graphs. So for every value of T, there's a K3T plus 2 minus 3 graph, which is not 4T choosable. Which means that if you somehow take the ratio of these things, this constant C in the conjecture of Kawarabayashi and Muha must be at least 4 over 3, these 4/3. This is a really nice construction, and it disproves that one additional color is sufficient. You need really a linear amount of additional colors here. And another conjecture, which is a bit weaker, by Kawarabayashi and Muha from 2007, when they also stated the existence of C conjecture, they actually said they believe that C equals 3/2 should work. And I mean, all these conjectures show you that somehow people have this intuition that it's a bit harder maybe than normal proper coloring, but the constant should be really small. It should be close to the Hadwiger conjecture, basically. So 3/2 times T was a conjecture, which was also appeared in some other survey articles. And my result now here is that this is not true. So I have a lower bound for this constant C, which is simply 2. So my theorem 3 proves that if T gets really large, then actually you need 2 minus little o of 2T minus little o of T colors. So close to 2 times T colors to list color KT minus 3 graphs. And I haven't phrased it explicitly like Barat, Jouré, and Wood. And there's a good reason for that, because my result is really only asymptotic. For small values of T, I get a really bad bound because I do some probabilistic method, and I needed some terms converge to 0, and they do so very slowly, unfortunately. So if you ask, for example, what is the best lower bound for T equals 10, I guess Barat, Jouré, and Wood would still beat me. But yeah, if T gets really, really big, then we can get close to 2 times T. And this raises, of course, a natural open problem or correction of this conjecture by Kawarabayashi and Muha. Maybe it is true that every graph with no KT minor is 2 times T choosable. 2 is at least a nice constant, so why not? Maybe this works. And another open problem, which is not known to be true now, coming not from the asymptotic side, but for very small values of T, is what is the best upper bound for K6 minus 3 graphs. We have seen by Thomason's and Trikovsky's result, 5 colors are good for K5 minus 3 graphs, but for K6, we don't know whether one more color is good or we need even 2 more colors, maybe. We don't know. I mean, I think we only know it's at least 6 and at most 8, so actually not even whether there are 7 choosable is known, and maybe there are 6 choosable. So this is also a nice open problem. Yes, so this is here my main contribution. But there's actually, as I said, my method constructs these graphs, these lower bound examples, using some randomness. And the same idea, actually, I later realized also works to refute some other conjecture. So there was also this conjecture by Woodle, 2 conjectures by Woodle. What happens if you don't exclude complete graphs, but complete bipartite graphs as minus? And so this is in a survey from 2001 on list coloring, where he mentions these conjectures. So both of them refer to KST minus 3 graphs. And what would we expect for them for the chromatic number, right? So KST is a subgraph of the complete graph on S plus T vertices. So if Hadwiger is true, then graphs of no minor of this type with S plus T minus 1 colors. But we can also not do better, because we can look at a complete graph of this order, and it doesn't contain this graph for size reasons. So this would be the natural conjecture in this case, which is actually just a weakening of Hadwiger's conjecture. If Hadwiger's conjecture is true, then this must also be true. Maybe this is an approach to prove something simpler, right? I mean, this is how this conjecture comes, that maybe this is simpler to prove for certain values of SMT. So also Seymour conjectured this. But then Woodle in the survey also mentions the same conjecture for list coloring. He says the same should be true for list coloring. And he also says some words about this conjecture, what is the intuition behind this. So, for example, he said that, he already knew that planar graphs are not for-choosable, so he knew that Hadwiger doesn't extend to list coloring, but he said maybe if we exclude something sparser, the structure of these graphs is strict, and we can actually get the same bound, the same optimal bound for the list coloring. And also he said somehow excluding KST is a natural thing for list coloring, because somehow what are the graphs which have large chromatic number? Yes, these are cliques, but you don't need to be a clique to have large list chromatic number, right? Also, the complete bipolar graphs are somehow canonical obstructions for list coloring. So in some sense, this makes sense. But yeah, as I told you, my method also disproves this second conjecture by Woodle. Let me directly go here. So Woodle's conjecture also fails asymptotically. So if you look at the KST minor free graphs, and S and T are really big and are of comparable size, so they are somewhat proportional, then the list chromatic number of graphs of no KST minor can be at least 2s plus t minus some little o terms. And this is, of course, much bigger than s plus t minus 1 if S and T are big enough, and refutes this conjecture strongly. But again, I mean, there's a very big weakness with this asymptotic approach, because my smallest counterexample to this conjecture of Woodle, I calculated, has 10 to the 10 to the 30 vertices, because things go really slowly to 0. And I mean, maybe I didn't optimize everything, but I mean, even if you optimize, I don't think you can get much better than this. And the smallest values of S and T for which it fails basically the exponent of the expression. So this is basically 10 to the 30 are the smallest values of S and T for which I can disprove the conjecture, which means that still there are many interesting cases of it. So for example, does RK44 minor free graphs 7 choosable? RK35 minor free graphs 7 choosable? These are like the smallest open problems for this. And these are still very nice questions, and I have no idea how to refute it using my approach. And asymptotically, again, if S and T are really big, what I conjecture could be true is that if S is the smaller of the numbers S and T, then 2s plus t colors could always suffice for the list coloring of KST minor free graphs, which would then be tied by my result, at least if S and T are big. So this is what I have here. But let me very quickly go back. I think I decided not to include a proof now for time reasons, but let me at least give you some history for this problem by Woodle as well, what we know for small values, because my result really just disproves for really insanely big graphs, which you will never encounter in reality. So I mean, okay, which graphs do we encounter in reality really? But okay, let's look at small values. What do we know there? So Woodle himself and also Chudnovsky et al. Proved that graphs with no k2t minor are t plus 1 choosable. And this is actually for a degeneracy reason. Graphs with no k2t minor, they always have vertices of degree at most t. And in his survey already, he proved that this result by Thomassen, that planar graphs are 5 choosable, extends to the larger class of graphs which have no k free minor. These include the planar graphs and are a bit larger. So this is true for these values. And then let's go a bit up with the t here. So Jurgensen proved that k free 4 minor free graphs are 5 degenerate and therefore 6 choosable. So also here this conjecture is true. And then if free is picked as a constant and t gets really big, then Kostoschka and Prince, they had a series of paper on this kind of graphs with no k free t minor, and they analyzed the density of these graphs. And from this, it follows that they are t plus 3 choosable, which is only off by 1 from the conjecture of Woodle, which says it would be t plus 2. And then there are also 2 other results which are not exactly tight, but give some evidence. So Jurgensen proved that k44 minor free graphs are 8 choosable, and Kawarabayashi proved in 2009 that k4t minor free graphs, so he also studied the conjecture, that k4t minor free graphs are 4 times t choosable, which at least proves a linear bound, which I think is not, it's not obvious. Yes, so this was the previous work on this conjecture and the density of these graphs with no KST minor. And somehow, yes, my examples show that you can still not get this tight result, which would somehow correspond to the number of colors required by Hadwiger's conjecture. So let me now conclude my talk. I have prepared actually a full proof of this probabilistic thing, but I think we all know that this was long enough. And I can summarize in a few words what is the main idea of my construction. So maybe let me go to a corresponding picture. So the main idea of my construction is basically that I construct certain bipartite graphs, which are obtained by randomness and which have some nice properties. And then So nice property simply means that if I have certain set connections in these graphs, there will be certain connections between the sets if there are sufficiently many of the sets. Okay, this is very abstract, but basically the sequence of graphs which I really care about and which I get from this has these properties phrased in this lemma, and they look as follows. So I can construct basically arbitrarily large of the graphs of the following type. So the vertex set of these graphs is partitioned into two cliques. So this basically means these are complements of bipartite graphs. And then these graphs in between those two cliques, this graph in between those two cliques is a very dense graph. It's almost complete in the sense that if I look at the vertex in one of the clique, for example, in A, and I look at its neighbors over to the other clique B, then it's connected to almost everyone except for a very small fraction, epsilon fraction of the neighbors, with epsilon times the size of B non-neighbors. So this is an almost complete graph. And I can still guarantee, although it is so close to being like complete, its maximum minor size, or the largest, that for reasonable values of S and T, it does not contain this KST as a minor. Or let's say for the construction of KT minor free graphs, I can basically construct these almost complete graphs with two cliques on 2T vertices, let's say, which don't contain a minor KT minor when T is just an epsilon larger, no K 1 plus epsilon times T minor. This is the kind of graphs I get here. And then, okay, let me go to the end of my construction. The idea of this construction is that there's this nice operation in graph minor theory, which preserves not having a certain graph as a minor, which is called clique sums. So if you want to construct graphs in a class of, for example, KT minor free graphs from given graphs which are already KT minor free, what you can always do is you identify cliques in those graphs and you merge them along the cliques. And this preserves KT minor freeness for rather simple reasons. So that's the reason why the graphs I construct have these two cliques, or that's what they are partitioned into, because I can basically take really lots of copies of these graphs I construct. So these graphs with A and B, which both form cliques and in between are almost complete. And let's say I identify them all in the clique B. So I take many distinct copies of this, and of those copies, I all identify them in this clique B. And because they didn't have large complete minors by my random construction, basically, I can still glue them together and they don't have large complete minors. But, and this is now the interesting thing, which is very different from this chromatic number and chromatic number. That's basically the whole point of this proof, is that by gluing things together along cliques, you can actually increase this chromatic number like very much, actually. And this is not possible for chromatic number. For chromatic number, there's some easy permutation argument which shows doing a clique sum operation does not increase chromatic number. But for this chromatic number, this exactly works. And basically, if you consider only one of my copies, it's actually roughly, I mean, it has no, okay, my construction has no minor of KT minor with T much bigger than the size of the two cliques, which are roughly of the same size N, let's say. And its chromatic number is only not much larger, also not much larger than N. So this is not a counterexample in itself. So this has chromatic number roughly N and largest clique number roughly N. But if I glue everything together, it's still Kn minor 3 or KT minor 3, if T is a bit larger than the size of B. But the list chromatic number will actually double. It will be almost as large as the chromatic number of a clique on 2 times n vertices. And how you can achieve this is by picking a clever list assignment. So maybe if you remember, these bipartite graphs, okay, these complements of bipartite graphs which I glue together are almost complete in the sense that if I look at any vertex in a set A, and I look at how many vertices in B is it not connected, it's at most an epsilon fraction of all the vertices in B. So only a small fraction of vertices in B it is not connected to. And now I can do this very clever list assignment, and this is actually not my idea, but this I stole in some sense from Barat, Jory, and Wood, who had a similar idea, but not as general for their construction. That I do the following list assignment. So for the, let's say B and A have roughly size n, I use in total 2 times n minus 1 colors, let's say, in my list. So colors from 1 up to 2n minus 1. And to the vertices in B, I simply assign the full list of colors from 1 up to 2n minus 1. But now what I do for the vertices in these A sets, which I glue together, or from the different copies I glue together, is very nice because they have size almost 2n minus this epsilon n. Because what I simply do is I say, if I have a vertex here in A, look at, okay, sorry, I forgot to say something important. So the number of copies we take here, which we glue together, is the number of 2n minus 1 colorings of B. So B must be somehow properly colored from 2n minus 1 colors I give to it. So now we want somehow for every possible coloring of the set B, which we could get, we want to have one corresponding copy of this graph, which we glue together, such that the list colors, or that the lists I assigned to these vertices in the set A correspond exactly to this coloring and then produce many conflicts. So let me make this more precise. So if, for example, I have this copy A of C1, which means that C1 is some coloring of the vertices in B, and A of C1 is a copy I assign for this coloring. Then if I have a vertex inside this A of C1, the colors I assign in this list are all colors except for those which appear in the C1 coloring of B on its non-neighbors. So I exclude the colors from the non-neighbors it has in B from its list. And the idea of this is very simple, because this means, okay, give me some coloring of B in your list coloring. Yes. So then let's say it's for some reason it's C1, right? It must be one of these many colorings. For each coloring, I have one matching copy. So let's say, for example, it's C1. Then every vertex, for every non-edge I sort of have between A and B, its endpoint still must have different colors, because every non-edge in this graph spanned by A of C1 and B goes from some vertex here in A to some vertex in B, and is one of these non-edges. And by definition, the left endpoint of such a non-edge did not include the color of the right endpoint in its list. So even if they're not adjacent, this way of choosing lists makes sure that even non-edges are properly colored. And then, because this was almost complete, I delete only a small set epsilon n of colors from each list in A. So there's still almost 2 n list assignments. But in effect, in this copy between A of C1 and B, it must be completely properly colored, because A and B are cliques. So these, anyways, by the graph coloring condition, must be properly colored. And all the edges in between are either real edges and must be properly colored, or are non-edges and are properly colored because of my list, because of the choice of my lists. So I don't know whether I conveyed this point nicely, because I didn't spend all the time now. But this is the main idea of the proof, that you do this clique sum operation, and it can double actually the list chromatic number for KT-3 case, and for the KST-3 case, some things change a bit, because you cannot glue on arbitrarily large cliques. You need to take a bit smaller cliques, but you can still disprove this conjecture by Woodle in the same way. Okay, so sorry for not planning the time well, and thank you for listening.